Hi there, everybody. Welcome back to another Chem Complete lecture. And in today's lecture, we are going to look at the hydration of alkenes, which is the addition of water to alkenes, using a strong acid in the presence of high heat. So we are going to get ready to take a look at that on the channel right now. So thank you so much for learning with Chem Complete today. And remember to head on over to chemcomplete.com for lots of free resources that can help you throughout your organic chemistry journey as you continue through your semester, as well as your STEM career. So getting into hydration of alkenes using an acid. The hydration of alkenes can be accomplished through the use of an acidic catalyst. Now, because it's a catalyst, that means we will regenerate the acid at the end of the reaction, and this needs to be accomplished under high heat. So what we have is some sort of a generalized alkene with the pi bond, and we will expose that to a strong acid and heat. Now, you can choose the acid of choice. I will typically use something like H2SO4. You have to be careful with things like HCl because you can get addition of the halide to the bond if you are using a substance like that. But generally what you're looking for is H3O+, because strong acids will fully dissociate into H3O+ when they're in solution. And then we use the triangle in order to represent heat for this reaction. And what we would end up with is an alcohol that is going to add to the carbon involved with the double bond. And then we would also get a hydrogen addition. So if you sum that up, you get H2O, which is why this is a hydration reaction. Here's the hydrogen, and then you would also have whatever is attached to the alkene at the start over there. Now, this method is primarily of industrial use, and that is because, number one, you're dealing with high temperatures and sometimes higher pressures in order to get around some of the very high temperatures. And then you also have to deal with strongly acidic conditions. So very corrosive, strong acids and high heat are not always optimal conditions for a smaller research lab or a student learning lab. And so many times this is reserved for industrial use, although you could do it in a smaller laboratory. All right, now looking at some of the regio and stereochemical consequences of this reaction before we look at its mechanism, you will get a Markovinkov regiochemistry outcome. And that is going to be observed where the OH, or the alcohol group, will be adding to the more substituted position of the alkene. However, there is a carbocation that is present in this particular pathway, and so due to that carbocation intermediate, the reaction is not going to be stereospecific in its outcome. In other words, we are not going to have 100% syn addition or 100% anti-addition. We're going to get a mix of both when it comes to the hydrogen and the alcohol group that adds. So let's take a look at the mechanism that would be involved in this. So we'll start with a 6-membered ring. We're going to make it an alkene, and then one of these two positions we will make a methyl substituent coming off. And that's just because we want to be able to look at the Markovinkov behavior in the outcome here. So heat is present, and then we are going to have the acidic conditions. So H3O+, which I am going to fully draw out here as H3O+. The acid itself is going to offer the hydrogen to the pi bond. So the pi bond will come in, it will seek out one of these hydrogens, and then the remaining electrons will go back to the oxygen in order to create water. So what this gives is an intermediate where a carbocation is present. Now, if we look at the two positions, the position in the upper right-hand corner, the one that has the methyl, is more highly substituted and therefore would have more hyperconjugation. So the hydrogen is going to add to this lower right-hand position, and then we would be left with a carbocation in the more stable carbocation position due to the extra hyperconjugation. So at this point, the water that was formed, or the aqueous environment which has water to offer up, is going to act as a nucleophile and will come in to this trigonal planar sp2 carbocation. So because it is trigonal planar, you could have the addition of the water in front of or behind the particular site of attack. So in other words, we again do not have a stereospecific outcome, but you would rather have a mixture in regards to the hydrogen and the hydroxyl group that's going to add. Now we will go ahead and show this coming in from the back here. So we've got a methyl group that would be present here. And then if this water does come in from behind, you need to make sure that you still show this as water. So in other words, it came in as H2O. We cannot just directly put the alcohol group there yet. There is going to be an additional step. And that also makes sense because we have to regenerate our catalyst. We haven't done that yet. So from this intermediate that we have here, and I'm implying the hydrogen that would be down in this position, I can use another molecule of water, and that water can then deprotonate the water that has added to the ring system. So this water will come in, it will grab this proton, and then these electrons can go to the oxygen to make it neutral instead of positively charged. And in doing so, I regenerate H3O+, which is important because the acid is a catalyst. I have to get it back at the end of the reaction. And then I end up with the final product. So the final product being that I would have the alcohol group, and again, the hydrogen, which is implied down there, has also added to the alkene. So I could get a final result of an alcohol functionality. The methyl group would still be there. And again, you would have a hydrogen that has added here, although we can show that as implied here. Okay, now the alcohol could add to the front or it could add to the back. Now, as far as stereochemistry, that wouldn't matter in this case because the example we gave, you do not have a stereo center here due to symmetry around the ring. However, you could get a mixture, a racemic mixture or a set of enantiomers if that is the case. So if you do have a differentiating factor there where the ring is not symmetrical all the way around. All right, now one of the other things that's important to realize is that because we're dealing with a carbocation, we can get rearrangement in this reaction. So carbocations have the ability to rearrange through what's either called a hydride shift or a methyl shift. So we'll go back to the same starting material and we will show you the hydride shift that could lead to this result here. So if I have the alkene, but this time I'm going to have the methyl group up here. So it's shifted by one position in the carbon and it's not actually attached to the alkene functionality itself. And then I go ahead and I use the same reagents. So I've got heat and I've got my H3O+. When you get ready to do this, the first step is going to occur as usual. So you would have the pi bond reaching out to this hydrogen, which is going to go ahead and give electrons back to the oxygen to form water. And what I would end up with is a carbocation in this secondary position right here. Right? The hydrogen has added here, but I have a methyl group that's present right here. So because there is a tertiary site directly next to this carbocation, the hydrogen that is also associated with this position can shift over. This is called a hydride shift. And the hydride shift is going to rearrange the carbocation so that it will go into the more stable tertiary position. So based on that hydride shift, I now have a product, or not a product, but an intermediate that's headed towards a product that would look like this. Here's the methyl group. I would have the positive charge in the tertiary position, and I would still have that hydrogen that added there. So from this point, I could now go ahead and I could add the water, and the mechanism would proceed as we have shown above. So the water will come in here, another water will deprotonate it, and then what I end up with is an alcohol group that has been put into a position that is one removed from the alkene itself. So you can see the OH group is now at this top carbon on the ring, right? And this position right here, which originally contained the alkene, it does have the hydrogen that added, but the alcohol has added to the position that was directly next to it due to a rearrangement of the carbocation, which is going to happen in situations where you could get better stability from a neighboring position due to its hyperconjugation, provided it has a methyl or a hydride, meaning a hydrogen, that it can shift. Okay, so just to wrap up here, there are other options for hydration of alkenes, and those include oxymercuration and hydroboration. And if you're interested in that, there is information on the channel for both of those reactions, both of which will have more stereospecific outcomes. So the oxymercuration and the hydroboration, neither of those are going to involve a carbocation, and they will have more specific outcomes as far as the stereochemistry is concerned. The oxymercuration will always give an anti-outcome, and the hydroboration will always give a syn outcome for the stereochemistry. So good things to keep in mind if you want to be more selective in your hydration process. So that covers hydration of alkenes using an acid catalyst along with heat. So thank you again so much for learning with Chem Complete. Head on over to chemcomplete.com for resources that can help you through your organic chemistry journey. Like the video if you found it helpful, because that helps boost us in the algorithm. And as always, subscribe if you want to be up to date with all of your STEM lectures as you are proceeding through on your career path. So again, thank you for learning with me, and I will see everybody in the next lecture.